Welcome to another episode of Dominic Does DIY. So today we're actually going to talk about the brushless motor design and how it operates so we can come to understand how we can control a brushless motor that we get off of Amazon or AliExpress or wherever. So of course there are many drivers out there that you can buy and they basically do this. So we're just going to go through the actual concept of brushless motor design and what it is that those chips are doing so that when you look at the chip and you try to spec one of those ICs out, that you'll know what it is that you're looking for and what it is that they're talking about. So we can get a good understanding of what the brushless motor controller is actually doing when you're turning phases on and off and when you want to turn phases on and off. And as always, like, subscribe, share the video. And now let's get into it and come to understand more about the brushless motor. So the first thing about the brushless motor, let's take a look at the motor itself so we can understand how it operates. So the motor contains a case, a rotor, a stator, and some Hall sensors. So the rotor is your magnet, which is actually also your driving force. That's the one with the shaft that goes outside of the motor itself. So as the rotor turns, that's actually the motor, that what we would consider the motor, right? The rotor spinning, and then you would put your fan or whatever you wanted, your gear, on the shaft of the rotor itself. And then so as the rotor would spin, then the shaft spins, and then you would be able to spin your gear, fan, whatever. That rotor is a permanent magnet that moves around based on the stator. The stator has windings in it, and then as you turn those windings on, you create an electromagnet, and you basically run the magnet of the rotor, you spin it around by controlling the rotation of the stator windings so that you basically run it like a magnetic rail train. Actually, in the earlier video, when I was showing the stepper motor and the DC brush motor, you can consider a brushless motor at a real low level, basically operate in the same manner as a stepper motor, right? So just like in the stepper motor, you would energize one of the coils, it would move one step, and then you'd have to energize the next coil to make it go to the next step, and then you'd energize the next cable to make it go to the next step. This is the same exact thing, except what we're going to do with the brushless motor is we are just going to very rapidly energize those coils so that we can spin this rotor at high RPMs. Rather than trying to control one step at a time, we're going to try to spin this thing at thousands of RPMs. So how do we know the position of the rotor? That depends on the Hall sensors that we got. And so the Hall sensors there are detecting the magnetic fields of the rotor. And based on the feedback from those Hall sensors, we can determine what coils we want to turn on in order to advance the rotor to its next position. So we just constantly see the changing Hall sensors. And as the Hall sensors change, we change our coil voltages and the coil current, which changes the magnetic field, which then spins the rotor. And that's all we're doing. We're just going to control the stator by moving the electrical field around to spin the rotor. In order to save me time on drawing pictures, I went ahead and downloaded this microchip app note, AN885. It's about one of their brushless motor controller ICs, but they go into the brushless motor design. And so, as we were saying, the whole idea is to spin the rotor by changing the magnetic field in the stator. So a stator is a motor wound in a Y formation like that with three phases. And as we know with inductors and motors, current cannot change instantaneously in the opposite direction. So if we want to move to a different phase, we always have to take into consideration that one of those phases, the current in that direction cannot change. So you can see here that in position 1, our A phase is our positive side of our power, and the negative side of our power, our DC minus, is the C phase. So we got current flowing from A to C. Then in step 2, when the rotor changes position and the Hall sensor triggers, we switch from going from A to C, we switch to picture 2 here, and our A phase still has the DC plus voltage, but we change the DC minus voltage to the B phase. So now our current flows, instead of A to C, we flow A to B. When our rotor moves and we sense the new Hall sensor position, the current through the B coil cannot change. So B still has to remain DC minus, but we move the DC plus from A phase to C phase. And so now we got current flowing from C to B. And likewise, this goes all the way around for these 6 rotations until you reach 6 and you see that DC plus is on the B phase, DC minus is on the C phase, and the next step again is number 1, in which A once again becomes the DC plus and C remained the DC minus to allow us to do a 360-degree rotation. So this is all we're doing. We are moving the current through these coils in this order in order that we can get the rotor to spin inside the stator. Now, in order to understand how to control the stator and the phase currents, we have to actually look at the sensor feedback. The Hall sensor feedback is what we use as information in order to understand how it is that we control the current through the coils in the stator. So we can see here, sensor A, B, and C, the 3 Hall sensors on the rotor, we can see that they are 120 degrees out of phase from each other, and that they are on for 50% duty cycle of the cycle. So 180 degrees of the 360 degrees, each one is on, but they are 120 degrees out of phase with each other. So now that we understand the basic concept of the brushless motor and the Hall sensors and how they function when the motor is spinning, let's look at the basic brushless motor control circuitry. So again, I'm using LT Spice to simulate this. Actually, if you look at previously I did an episode on FETs and motor controls, and I had a simpler H-bridge version. So I basically stole this whole motor setup from them. So I'm using the same 24-volt motor setup from that assortment. I've just turned it into 3 phases instead of 2. Also, because I'm doing this in LT Spice, you can see that my FETs are being controlled by H1, H2, H3, meaning the high side FETs, and L1, L2, and L3, which is the low side FETs, and I've got some pull up and pull down resistors, but these would normally be controlled by a brushless motor controller, a microcontroller, or something like that, and they wouldn't have these pull ups, pull downs in the circuit itself. So this is our brushless motor simulation. We use the same setup from like I said, the FET motor driver circuit episode. So we got our inductor, the resistor, the back EMF going on. And so each of these sections are part of the Y transformer for the brushless motor. So you can see you have phase A, phase B, and phase C. And then these are all the motor coils that are going into the center of the Y transformer. The section on the right is just to capture the feedback voltage of the motor itself in the circuit. Looking back at the control circuitry with the microchip app node open, we can see our A, B, and C phase on the coil. And so this is what we are trying to do. We turn the high side on. So the high side is going to be our DC plus, and the low side is going to connect the coil to DC minus. So in section 1 right here, where we have it going from phase A to phase C, that would mean that we would want to have H1 on, which would allow the V motor to go through the A phase, and then we would want to turn on low side FET 3 in order that the current could exit phase C through the low side FET M7. Likewise, as we moved to position 2, we would then want to shut off the low side FET M7, and we would want to turn on the low side FET M2 to allow current to go from phase A to phase B. So now let's take a look at how all this works together. There's sensors and the high side and low sides FET controlling the current going through the phases. So we know that in order to get current flow, we need a high side and a low side across the phases, meaning a V plus and a V minus. So one of the phases will have V plus connected to it, and another one of the phases will have V minus connected to it. Then how do we set these states based on the Hall sensors? Well, let's take a look at phase A, and we can see that when phase A is V plus, meaning the high side FET M3 is on, if we look down at the sensors, this happens when you have sensor A high and sensor B low. When those two conditions are met, then we can see that phase A will be connected to the high side, the DC plus. Then what about the minus? So we can see that the low side FET for phase A, M6, we can see that it becomes active in sections 3 and 4 here, and that becomes active if we scroll down to the Hall sensor. If we scroll down to the Hall sensor reactions, we can see that that is active when the sensor B is high and sensor A is low. So they kind of mirror each other, right? It's DC plus when sensor A is high and B is low, and it's DC minus when sensor B is high and sensor A is low. And actually that goes across the board. So if we take a look at phase B, we can see it kind of tends to the same thing. We can see that sensor B becomes DC plus, gets connected to DC plus, meaning our high side FET M1 is on when sensor B is on and sensor C is off. And likewise, we can see that phase B, the low side FET M2 is turned on and it is connected to DC minus when sensor C is high and sensor B is low. So all we got to do to make this motor spin is take a look at the sensors and then have the high side and low side FETs of the phases react appropriately. So first, let's set up inside our LT Spice because I don't have an actual motor that I can run, and I don't have enough, and I don't have a scope with enough probes to be able to probe all this stuff at the same time. But we can take a look through LT Spice and kind of see how the brushless motor goes by having the Hall sensor set up as DC supplies to turn the system on and off. All right, so I got my Hall sensors here set up, V11, V12, and V13. These are my Hall sensors, Hall sensor A, B, and C. And how do I got them set up? I got them set up to pulse. If we take a look at it, I have to use a 24 volt pulse because the PMOS on the high side of the FET, remember this 24 volt motor that I'm trying to run, so to turn off that high side PMOS, I actually have to have a 24 volt input on the gate. So I'm going to pulse this Hall sensor at 24 volts. Normally you're going into a microcontroller or something else, and this Hall sensor is actually outputting either a 3.3 volt signal or a 5 volt signal. But for this LT Spice simulation, we're just going to go ahead and have it output 24 volts so I don't have to do something too crazy. And what am I going to do? I'm just going to give a 1 millisecond delay, and my T on is going to be 180 microseconds, and my period is going to be 360 microseconds. So you can see here, when we look at the Hall sensors, it's a 50% duty cycle on each of the phases. But remember, they are 120 degrees out of phase. So what did I do for phase B? Because this is phase A, so you can see my time delay is 1 millisecond for Hall sensor B. You can see I've still got the same duty cycle, T on for 180 microseconds, and my period is still 360 microseconds. But in order to get that 120 degree out of phase sequence, I just did a time delay of 1.12 milliseconds in order to create that 120 degree phase shift. For the Hall sensor C, same thing. I got my T on at 180 microseconds, my period at 360, but I did the T delay at 1.24 milliseconds to make it again 120 degrees out of phase. Then all I did with those outputs is I just used some logic gates. But you can see here, phase A is 1, phase B is 2, and phase C is 3. So you can see it at our sensors. What did we say? We said we wanted the high side FET to be on when we have Hall sensor A high and Hall sensor B low. So I'm taking a look at Hall sensor A being high and Hall sensor B being low. Going into an AND gate, I just put it through a NOT gate right here. And I chose the inverting output because remember it's a PMOS. So if I want to turn it on, I actually got to put the gate to ground. So I'm using the NOT gate so that when I get an AND situation, it becomes a NAND and it'll shoot my thing low. And when it's not true, it'll put it high to turn the FET off. And then the same thing with all of these. As you can see, they're all the same thing. It's one Hall sensor is high, one Hall sensor is low. And just like we discussed, for phase A, it is either the high side is Hall sensor A is high and Hall sensor B is low. And for the low side, it just flips Hall sensor A and B. So we're looking for Hall sensor B being high and Hall sensor A being low. And then the same thing for phase B, except the Hall sensors that we're looking at is Hall sensor B and C. The same thing with phase C. We're looking at Hall sensors A and C. So let's go ahead and run the simulation and just take a look first at the Hall sensors to make sure that the timing on those is accurate. So here we can see, exactly as we expected, we got a 50% duty cycle on all the Hall sensors, and we are 120 degrees out of phase between A, B, and C. So this is exactly what we want to see. If this motor was spinning, this is exactly what we would see. Now, as the motor spins faster, the T-on and the period are going to decrease, and then of course as the motor spins slower, then the T-on and the period are going to increase. But ultimately you will still have this overall look when you start comparing the three phases, right? They will be 50% duty cycle and they will be 120 degrees out of phase. So now that we know that our Hall sensors are working as expected, now we got to check out the gate controls. Remember, these Hall sensors are then going to feed into our controller. The controller is then going to turn the high side and the low side FETs on of the phases in order to make the rotor spin by controlling the magnetic field in the stator. So now let's run it and we will check out the high side and the low side FET outputs. So now if we start breaking down our timing sequence, our drive timing, with what we're seeing on the screen, let's take a look and see if we can pair up what cycle we're in with what we're actually seeing on the screen here. This is phase A, this is phase B, this is phase C. So let's take a look and start and see which one is the first one that has the high side FET on. So if we look here, we can see that H3 is the first one to go low. So this means that our high side FET is on. And if our high side FET is on, let's see which one is low when H3 goes low. If we go up to phase A, we can see that the low side FET of phase A is high. And remember, the low side FET NMOS, the reason you see the voltage differential is because I only need 5 volts on the low side FET to turn it on, but I need 24 volts on the high side FET to turn it off. So that's why the low side FETs go from 0 to 5, and the high side FET goes from 24 to 0. But we can see here, phase C, when it goes low, phase A turns on. So if we go over to our chart, that means that C is V plus and A is V minus. So that means that right now we are in section 3. So then the next cycle should be 2. So what is 2 going to do? 2 should then have C still at DC plus, but now we should turn off the low side FET of A, and we should turn on the low side FET of B. So if we go over here, we can see when phase A, low side FET turns off, immediately our low side FET on phase B turns on. So now this is section 2. Then after section 2, what do we see? Section 2 should be 1, which means our A side gets DC plus, so the A side goes, high side goes low, and our B side, low side FET should still be turned on. And so we see it is. So we can see it starts at 3, goes to 2, goes to 1, and as we continue on, we will see it go 6, 5, 4, and then repeat. So we got our FETs are being controlled as they're supposed to, so that we can get the output that we expect. So the Hall sensors are now controlling our gates. So now our simulated brushless controller is looking like it's working properly, right? We're getting the Hall sensor inputs, and those inputs are then outputting to the high side and low side FETs to allow us to turn the phases on in the proper order to cause this thing to spin. Now comes the meat and potatoes of this whole thing, right? This is our actual brushless motor driver circuit, right? We have our V motor. This is our DC supply. These are our high side FETs, our low side FETs. We have a current sense resistor here in case we wanted to measure current. And now we know we've got our Hall sensors spinning as they should. We got our high side and low side FETs turning on as they should. So let us take a look. What is the output of this three-phase motor looking like? So you can see here our sinusoidal wave, and right now we're pushing current, peaking up at 6 amps and going all the way down to minus 6 amps. And you might think, oh, well, where's the negative 6 amps coming from? But you got to remember the way that this probe is measuring, right? Current is always directional when you're measuring for current. So you can see, looking at these drawings, phase A in sections 1 and 2, they are having current flow in one direction, which would give us a positive 6 amps. But looking at 4 and 5, steps 4 and 5, we can see the current is flowing in the other direction, right? The opposite direction. But my probe direction isn't changing. So because my direction on the coil changed, then I'm going to read a negative current on the output of this simulation. I hope you enjoyed the intro to brushless motors and how to control them. And if you have any questions, feel free to comment down below and I'll try to get to them. But until next time, I hope you have a good weekend. It's 4th of July. So do whatever it is that you like to do, because I know it's a 4-day weekend for a lot of people. So go do something patriotic, like blow something up, because that's what 4th of July is for. Shooting off fireworks and starting fires. So enjoy yourself, and I'll see you on the next episode.